for free fall questions and problems. Problem 6. The best rebounders and slam dunkers in basketball have a vertical leap. That is the vertical movement of a fixed point on their body, because their body can kind of crouch and stuff. We're just saying, some point that can be wiggling around. So maybe like the bottom of their foot, of about 120 centimeters. What is their initial launch speed off the ground then? How fast are they going when they come back to the ground, and how long are they in the air? So this is a lot like problem 4, the kangaroo jumping problem. My tailless kangaroo that I drew, and you say, what's their initial launch speed off the ground given this data? So we're going to go ahead and sketch this. So again, we're going from them starting off kind of crouched, right? Right? And they start off kind of crouched down, and then they are going to kind of spring upward. Oops. Right. Anyway. Right. They're going to kind of jump up. Maybe they're leaping, trying to grab the ball, perhaps. Anyway, good enough. Okay, so, but when they leap, they're going to jump 120 centimeters. That's impressive, right? That's over a meter, right? Which is like, over 3 feet, 3 inches. 120 centimeters, so that's impressive. So they're going to jump. Holy cow, like that high. That's impressive. So 120 centimeters. The first thing I'm going to do is recognize that this variable for length is centimeters, and we know that we typically in physics like to use meters for our unit. So I'm going to right away convert that. I know that 100 centimeters are a meter, so I know that is 1.2 meters. Okay, and so that's like the highest. That's as high as, like, if I go from the bottom of their foot, that's how high it's going to get up in the air. So take a look at this. We want to know our launch speed off the ground. So we're trying to find our speed as we take off down here, how fast they're going when they come back to the ground, and how long they're in the air. So to do this, they give us information about this location. They give us information about this location up here. So I'm going to make this my starting location, ending location for my first calculation. So I'm going to calculate from takeoff to peak is what I'm going to do here. And they're going to, as they take off, they're going to start off going really quickly. And that's that V naught I'm trying to find. And they're going to get slower and slower as gravity slows them down until they get to their peak. Let's list our knowns. And we'll say, listing my kinematics variables, A, V naught, V, displacement, and time. It, of course, is my son Andrew's birthday, and it's time to sing happy birthday. So I better go do that. So I will be back. All right, so back for problem 6. Got my my birthday cake from Andrew's birthday, and I'm all set to go. So here we are. We decided that we were going to go from ground to the peak. So this calculation is ground to peak. And we say, hey, when he's in the air, the only force acting on him is gravity. Like once he takes off and leaves the ground, that's our starting point, when he leaves contact with the ground. Then the only thing acting on him is the earth pulling down on him. So our acceleration is going to be negative 9.8 meters per second squared. We know his initial takeoff speed. That is what we're trying to find, initial launch speed off the ground. So put a little question mark there. His final velocity, we're going to the peak. And one thing we know about the peak is that is where we are changing directions from going up to where we change to going down. So our velocities are going to go from being positive to being negative. That means they have to pass through 0. 0 is your velocity at the peak. And you say displacement, we know that going up, we know that the displacement is 1.2 meters. That's what they told us. And so you say, well, gosh, that's 1, 2, 3 variables, looking for the fourth. I would want the formula that doesn't have time in it, right? That would be this one. V squared is V naught squared plus 2a delta x. And I can solve that pretty quickly here. We're trying to find V naught, so maybe I'll rearrange it to get V naught by itself. I'll subtract that 2a delta x and then take a square root. So I'll have V squared minus 2a delta x, square root of that. That will be V naught. So that's what my formula looks like. I can substitute in some values here. My final velocity is 0 at the peak, so that whole term just drops out. So it'll be the root of minus 2 times negative 9.8. You say, oh, that negative, they're going to cancel. Times delta x of 1.2. Okay, don't want to have a negative under the radical, so that's perfect. Punch in my calculator. 19.6 times 1.2. Take square root. And I get we'll round that off to 8.5 meters per second for V naught. So that is my initial launch speed as we take off from the ground. Part B asks, how fast are they going when they come back to the ground? Well, we'll recall, we explored this back in problem 3. We said this is one of those special cases we talked about, problem 3. 5 things to know about uniform vertical motion. When we take off, go up, and end up coming straight back down, and ending up at the height that we started at, that's what's going to happen here. You're going to jump up and end up landing back on the ground. And so you say, how fast are they going when they get back to the ground? We know that at any given height, these velocities are equal and opposite. So if our velocity taking off was 4.85 meters per second, then our velocity when we end up back on the ground, that final velocity will be equal, but opposite will be going down, so negative 4.85 meters per second. Okay. And again, if you want to see the justification behind that fact, we talked about these things on problem 3. And you definitely need to be aware of this. This is very, very useful and important information. Part C, how long are they in the air? Well, that's the time it takes to go up to the peak and the time to come back down from the peak. And again, we know something special about that. We know that the time to the peak is half of that total time. So I can just calculate the time to the peak and double it, and that'll be the total time. So I'm not going to do a new chart. I'll just go this one, ground to peak, solve for the time, and double it. Now, I now know V naught, so I have that value. So I have this, and this, and this, and this. I got all the variables except T. What might be a nice equation to use, an easy one to solve? How about if we use V is AT plus V naught, and solve for that T, rearranging. T would be V minus V naught over A. Substituting my values. Final velocity, again, are we just going to the peak and doubling it? That's the plan. Final velocity of the peak is 0. Minus my initial velocity, 4.85. Solve for that back in part A. Divided by acceleration, negative 9.8. Once again, the negatives are going to cancel, and I'll get a positive answer out for time. That sounds good to me. 4.85, I just got it in my calculator already, divided by 9.8, and I get 0.495 about. But this was me going from ground to peak. I want the total time to go up and then down. The time to the peak is half the total time when I return to the same height. So I can just double this. So I'll punch that in my calculator, I'll double it, and I'll get 0.99 about. Rounds off to 0.99 seconds. So that is the total time in the air. And that is problem 6.